All that diving we did the last time has flooded my brain with all kinds of information. I'm sure you're the same. What are we going to do with all this info to remember? Shh. I think we're going to need a cheat sheet. Oh. Wait. What? So you think I've lost it? Well, not really. The cheat sheet I'm talking about is none other than the chemist's best friend, the periodic table. Study it. Understand it. Know it. Well, like me, you may want to carry it with you. And it will help to carry you through the rest of the year. In this lesson, you will describe the development of the periodic table as a result of the contributions of Mendeleev and Moseley. Being a scientist in the 1860s, all of the discoveries about the atom were very exciting, yet at the same time a little overwhelming. So, scientists tried to find a way to organize the elements. This process led scientists to discover that certain groups of elements all shared similar properties. The early chemists had similar thoughts. They grouped the elements according to similar properties, which provided a little bit of organization, but not quite enough. One of the problems was that the chemists were not using a uniform method for determining the atomic masses of the elements. Remember what happens when there are too many variables? In September 1860, a group of chemists assembled to settle this issue. It was then that major discoveries regarding the organization of elements began to happen. The students have done precisely what Dmitri Mendeleev did back in 1860. He also used note cards, on which he wrote the name of an element, its known atomic mass, and a list of its properties. He then arranged and rearranged the note cards, looking for patterns. He found that arranging the elements according to atomic mass made the most sense, because the properties of the elements repeated at regular intervals, or periods, thus the name periodic table. He left some blank spaces in his table to make the properties and masses line up. He even predicted the properties of those missing elements, and he was correct. When scandium, gallium, and germanium were discovered, they had properties very similar to the properties predicted by Mendeleev. What do you know? Sneaky old Mendeleev fudged as well. He placed iodine with an atomic mass of 127 after tellurium with an atomic mass of 128, because doing so placed these two elements in the correct groups according to their properties. Now, don't get me wrong, Mendeleev did amazing work. In fact, most people give him credit for discovering the periodic table. But, as often occurs in scientific discovery, his amazing work raised a tantalizing question. Why was it that a few elements did not seem to fall into the right place if arranged by atomic mass? And the scientists were off again, researching and investigating, looking for the answer to this question. About 40 years later, an English scientist named Henry Moseley discovered that all of the atoms of an element had the same number of protons, and this led to the modern definition of atomic number. Remember that an element's atomic number tells the number of protons in the nucleus of the atom. Moseley also discovered that it made more sense to arrange the elements by atomic number than by atomic mass. When the elements are arranged by increasing atomic number, the properties of the elements repeat, just like they did on Mendeleev's table. But there is no need to fudge. Remember, when Mendeleev arranged the elements in order of increasing atomic mass, in a couple places he flip-flopped and placed the heavier element before the lighter element, so that the elements would be in the correct group according to their properties. However, when the elements are instead arranged in order of increasing atomic number, no fudging is necessary.
The periodic table today reflects the work of both Mendeleev and Moseley. The result of their work is known as the modern periodic law. The modern periodic law states that the chemical and physical properties of the elements are periodic functions of their atomic numbers. Periodic function just means that something repeats according to a pattern. So another way to state the modern periodic law is to say that the properties of the elements repeat in a pattern when the elements are arranged by increasing atomic number.
Of course, the scientists couldn't stop there. Now that they had found a way to organize the elements, they wanted to know why. Why do the properties repeat? What is it about the elements in each column that makes them behave similarly? We're going to do a little investigating to see if we can't figure out the answer to that question. Let's review what we know about an element's chemical nature.
Each element has a certain number of protons in the nucleus that determines its atomic number. Each element has an atomic mass, which is accounted for primarily by the protons and neutrons in the nucleus.
Each element has an equal number of electrons as protons in a neutral atom. The arrangement of the electrons is seen by an element's electron distribution.
Very good. Now that we understand how the periodic table evolved and why it is organized the way it is, let's get back to some more ways we are going to use it as a cheat sheet. I know you think I'm exaggerating, but if you understand the organization of the periodic table, it will be an amazing resource to you.
In this lesson, you will use the periodic table to define the word period, determine the number of energy levels in an atom of an element, define the word family, determine the number of valence electrons in an atom of an element, determine if an element is a metal, non-metal, or metalloid, determine if an element is a solid, liquid, or gas at room temperature, and state an element's family name.
We already know that each element square on the periodic table gives useful information about that element. But the manner in which the table is organized also gives useful information. That is what we are going to investigate in this program. The first thing you want to notice about the periodic table is that it is organized into rows and columns. Let's start by talking about the rows. Remember how we said that the properties of an element repeat in a periodic way? Well, the rows are called periods.
A row on the periodic table is called a period. There are 7 rows. An element's row number tells us the principal quantum number for the outermost electron of that element. So an element in period 2 would have a principal quantum number of 2, and its outermost electron would be on the second energy level.
Let's take a closer look. Your local teacher is going to give you a blank periodic table and some colored pens or pencils. Throughout this program, you will want to fill in your table as Mary fills in hers. Whenever Mary uses a new color, you will want to use a new color as well. Now, you do not have to use the exact same colors in the exact same places, just a different color for each topic we discuss. Here we go. Let's number the 7 rows on the periodic table. The first row is number 1. The second is number 2, and so on and so on. Remember from our last program that the 2 rows on the bottom fit into rows 6 and 7. They are merely pulled out to save space, so don't label them 8 and 9. Label them 6 and 7. Now, let's talk about the columns on the periodic table. Remember how we found that all of the elements in a column share a similar electron configuration and similar properties? Because of this, a column on the periodic table is called a family.
A column on the periodic table is called a family. There are 18 columns. Columns 1, 2, and 13 through 18 are considered the main block of the table. The number in the ones place for these columns indicates the number of electrons on the atom's outer energy level, or the number of valence electrons. So an atom of an element in column 2 has 2 valence electrons, and an atom of an element in column 15 has 5 valence electrons.
let's number our families. Are you using a different color? We just start on the left with number 1 and go all the way across until we get to number 18. To help you remember that the number of valence electrons corresponds only to the number in the ones place, we will highlight or circle that number for each family. Before we go on, let's get a little use out of our cheat sheet, the periodic table, by answering a few questions. You do not need to write these down, but you do need to use your periodic table to figure them out in your head. How many valence electrons would an atom of magnesium have? And what would be the energy level of the valence electrons? Here is magnesium. Since it is in the second family, it has 2 valence electrons. And since it is in the third period, it has 3 energy levels. Let's do one more before we expand the usefulness of our cheat sheet. How many valence electrons and energy levels would an atom of bromine have? Bromine is in the 17th family, so it has 7 valence electrons. It is in the 4th period that corresponds to 4 energy levels. See how easy it is with the periodic table at hand? If you had to memorize that information for every element, ugh. But thank goodness for our cheat sheet. And believe it or not, it tells us even more. There are certain properties of elements that relate to whether the element is a metal or a non-metal. And, of course, the periodic table is right there to give us that information. Let's draw in this zigzag line on the periodic table. This line is often called the metalloid line, because most of the elements along this line are known as metalloids.
Metalloids are elements that are not clearly metals and are not clearly nonmetals. They have some characteristics of both metals and nonmetals, with the exception of aluminum, which is a metal. The elements that lie along the zigzag line are the metalloids.
Let's go ahead and write in the symbols for the metalloids. Boron symbol is B. Silicon symbol is Si. Germanium is Ge. Arsenic is As. Antimony is Sb. Tellurium is Te. Polonium is Po. And astatine is At. But what about the rest of the elements? Well, everything to the left of the zigzag line is a metal, and everything to the right of the zigzag line is a nonmetal. So let's look back at our 2 examples from earlier. Magnesium lies to the left of the line, so it is a metal. And bromine lies to the right of the line, so it is a nonmetal. Another useful thing to know about an element is whether it is a solid, liquid, or gas at room temperature. This one isn't as cut and dried on the periodic table, but the cheat sheet will still help you in remembering these. There are only 2 elements that are liquids at room temperature. They are mercury and bromine. All of the gases on the periodic table are near one another, with the exception of hydrogen. The other gases are nitrogen, oxygen, fluorine, chlorine, and all of the elements in family 18: helium, neon, argon, krypton, xenon, and radon. All of the other elements are solids at room temperature. Now that we can use the periodic table, our favorite cheat sheet, to find some basic information about each element, let's talk some more about the various families on the periodic table. Just like you share common properties with people in your family, no, really, whether you like it or not, you do. Well, the elements share properties with other elements in their families. And just like your family has a name such as the Smith family, the elemental families have names too. Family 1, to the far left of the periodic table, is known as the alkali metals family. The only exception is hydrogen. Hydrogen sits on top of this family because it shares a similar electron distribution, but hydrogen is really a family of its own.
Alkaline metals. These elements are so reactive that they are never found in nature outside of compounds. Further, the elements sodium, lithium, and potassium are never found in their metallic state because they are so reactive. For example, when exposed to air, pure sodium rapidly turns into sodium oxide, and when exposed to water, sodium reacts violently, producing sodium hydroxide and hydrogen gas. The compounds created from the alkaloid metals are often quite unlike the alkaloid metals that form them.
The next family, column 2, is known as the alkaline earth metals family. This family shares some similar characteristics with the alkali metals.
The members of Group 2 are called alkaline earth metals. Alkaline earth metals are the second most reactive metals and are not typically found naturally outside of compounds. Most importantly, magnesium is found in chlorophyll molecules, which are critical to the process of photosynthesis, which is the basis of life on Earth. Both magnesium and calcium have a great value in industry. Alloys of magnesium are very strong and light, making them ideal for use in aircraft and automobile parts. Calcium is used in making steel and acts as a hardening agent in lead. In nature, huge deposits of calcium carbonate occur in rocks such as limestone and marble. By placing limestone in a kiln, lime, which is used in cement and concrete, can be formed.
Columns 3 through 12 are all members of the family known as the transition metals. These metals behave similarly because they all have electrons filling a d sublevel at the end of their configurations.
In the transition metals, some groups are of particular interest. For example, Group 6 contains some of the hardest metals known to man: chromium, molybdenum, and tungsten. All of these metals are capable of producing extremely hard alloys when combined with other metals, although tungsten is particularly hard even by itself. Chrome is used in making stainless steel and is a highly reflective plating. Tungsten has a high melting point, about 3,460 degrees Celsius, or about 2 times that of iron. Tungsten is often used as a filament in light bulbs and the production of ultra-hard tungsten steel. The first member of Group 8, iron, is a particularly important element that has been widely used in manufacturing since the Industrial Revolution. Iron is the second most abundant metal next to aluminum, but is much easier to obtain from its ore than is aluminum. The relative abundance of iron, its ability to be magnetized, its strength, and its ability to be easily combined with other elements to form alloys make iron and its derivative steel the most used metal in the world. In an uncombined state, iron is rather reactive to moisture and salt in the air and forms an oxide we call rust. This is often overcome by combining different metals with iron to form rust-resistant alloys. For example, cast iron is an alloy high in carbon and silicon, which is resistant to rust. Chrome and iron are combined to form highly corrosion-resistant stainless steel. Another group of metals are the elements found in Group 11, which contains copper, silver, and gold. These elements are often referred to as the coinage metals, as their resistance to corrosion makes them ideal for use as coins. All of the coinage metals are also excellent conductors of electricity. The majority of electrical wire contains copper, and the contacts of high-quality audio and video equipment are often gold-plated. The combination of high conductivity and corrosion resistance explains why the contacts that trigger automobile airbags are gold-plated. Silver nitrates are critical to the creation of photographic images. The members of group number 12 are also highly corrosion resistant. This group includes zinc, cadmium, and mercury. Less reactive than iron, zinc is often used to coat steel to prevent it from rusting. This process is known as galvanization. Mercury is unique as a metal because it is liquid at room temperature. Its conductivity makes it ideal for switches that need to be activated by the movement of a fluid, such as thermostats. Mercury also has uses in dentistry. Amalgams, which are alloys of mercury and silver, are used for filling decayed tooth surfaces.
Families 13 and 14 have more variation in their properties because they contain metals, nonmetals, and metalloids. These two families are usually referred to by the element on top, the boron family and the carbon family.
Members of the groups 13 and 14 probably contain the most varied members of any of the groups of elements. The two most important members of group 13 are boron and aluminum. Boron is a metalloid that has properties of both a metal and a non-metal. Boron is a semiconductor of electricity. It is commonly used in the control rods of nuclear reactors. Aluminum is a very lightweight and strong metal and is also a very good conductor of electricity. The dull finish associated with aluminum is caused by a self-oxidizing feature that protects it from corrosion and deterioration. Used in a variety of applications, aluminum is the most abundant metal on Earth. Alloys of aluminum are used to make cooking utensils, car and airplane parts, and recyclable beverage cans. The first member of group 14 is carbon, perhaps one of the most important elements of all. Carbon molecules are found in all living things. Once, scientists theorized that only living organisms were capable of producing carbon compounds. Thus, the branch of chemistry that studies carbon bonds is called organic chemistry. It was carbon-based fuels, such as coal, that helped provide the energy to power the Industrial Revolution. Coal, oil, and gas are still burned in the majority of electrical power plants today. Carbon shares group 14 with the elements silicon and germanium, which are metalloids used as semiconductors in computer chips, and tin and lead, which are stable metals. Tin and lead are resistant to corrosion. Tin is often used, like zinc, to plate metals. Lead cannot be used to plate other metals due to the danger of lead poisoning. Once used in paint as a color pigment, lead is no longer used in paints due to studies indicating lead poisoning can occur if paints containing lead are inhaled or eaten by small children. It has been hypothesized that lead poisoning was one of the first types of environmental pollution, as the Roman Empire used lead in ceramic glazes and the lining of aqueducts which carried much of the empire's drinking water. However, lead is useful in a variety of other applications, including its ability to reflect radiation due to its dense atomic structure. Also, because of its weight, lead is used in producing leaded glass and crystal, both of which have a resilient luster and a heavy, solid feel.
Family 15 also is named according to the element on top. It is known as the nitrogen family. It also has some varying properties because of the metalloids.
Group number 15 is the nitrogen family. Nitrogen is relatively unreactive, and 80% of the Earth's atmosphere is uncombined nitrogen gas. Although nitrogen is very stable in its elemental form, most of the compounds it forms are not. Nitrogen compounds include gunpowder, nitroglycerin, dynamite, and TNT. Phosphorus, which is also a member of the nitrogen group, is highly reactive in a combined or uncombined state. Uncombined phosphorus ignites spontaneously at room temperature with oxygen. As phosphorus oxidizes, it gives off a phosphorescent glow. Not surprisingly, phosphorus is used in producing such products as matches and road flares. Both phosphorus and nitrogen compounds are used as fertilizers in agriculture. Nitrogen is often applied in the form of ammonium nitrate fertilizers. The phosphates in household and industrial detergents enter waterways because most water treatment facilities are unable to break them down completely. The result is sudsing discharges from water treatment facilities which promote the heavy growth of algae and other plant life in waterways that can cause the destruction of competing organisms in the waterway.
Family 16 is called the oxygen family. Again, it gets its name because oxygen is at the top of the family. You could say that oxygen is the head of the family.
Group 16 is the oxygen family. Unlike nitrogen, oxygen, which composes 20% of the atmosphere, is highly abundant in compounds and is found in combination with almost all the other elements. The compounds that oxygen atoms form with carbon atoms are critical to life on Earth. Sulfur has similar qualities to phosphorus, which is right next to it on the periodic table. Sulfur is found under beds of quicksand in Texas and Louisiana. Sulfur is used in products like matches and fireworks, and also in drugs, fungicides, and insecticides. However, the principal use of sulfur is in the production of sulfuric acid. Sulfuric acid is used in almost every industry, in the production of products like fertilizers, steel, gasoline, paints, dyes, plastics, textiles, explosives, and batteries.
Family 17 is known as the halogens. The word halogen means salt former, and the elements in this family readily form salts with metals.
The members of Group 17 are referred to as the halogens. All the members of this group are so active that they do not occur in an uncombined state in nature. Chlorine and fluorine are often combined with water. Compounds of fluorine are added to the water to help the human body produce other compounds which strengthen teeth and bones. Chlorine is added to disinfect and purify water supplies and swimming pools. Iodine is a crucial element to the functioning of the thyroid glands in humans. In seawater, all of the halogens can be found in abundance.
The last family, column 18, is called the noble gases. You will recall that all of these elements are gases at room temperature, so that part of the name makes sense. They are noble because they don't react very readily with any of the other elements.
The last group of the periodic table is the noble gases. These are the least reactive of all the elements. Because of their stability, the noble gases are useful and safe for a variety of applications. Helium is often obtained from natural gas wells and is used to inflate weather balloons and huge airships. Helium is excellent for filling balloons and airships since it is non-flammable. Earlier in history, hydrogen was used to lift great airships, but hydrogen is a highly flammable gas, which always presents the potential for disaster, as in the case of the Hindenburg. Argon and neon are used to produce the dazzling colors of neon signs and lights found on storefronts and along the Las Vegas Strip. Helium, argon, and neon are often excited by electrical charges to produce laser lights.
Let's not forget the elements at the bottom of the table. They are known as the lanthanides and actinides. This is easy to remember because the element at the beginning of the lanthanides is lanthanum, and the element at the beginning of the actinides is actinium.
At the bottom of the periodic table are members of periods 6 and 7 that have electron configurations unlike any of the other elements of the periodic table. Few of the elements contained at the bottom of the periodic table are used very often in a way that relates to our day-to-day existence, with the exception of uranium, which fuels nuclear power plants, and plutonium, which is used in nuclear weapons. Elements at the bottom of the table that would be members of period 6 are called the lanthanide series, or rare earth elements, because of their scarcity in the environment. Uranium and plutonium belong to the actinide series, which is part of period 7. Other radioactive elements that have been formed in atomic laboratories are also members of the actinide series. Large amounts of uranium are mined in western Colorado, Utah, and northern Canada.